Welcome back to Fossil Fundamentals, a web series all about fossils. Here in our 4th episode, we will be talking about the different types of fossils you can find and showing you some great examples. So stay tuned and let's dive into the fascinating world of fossils. Chapter 1. Body fossils. Body fossils represents the actual remains of a past organism, such as bones, teeth, shells. These are created when an organism dies and is quickly buried by sediment. Over time, the remains can become mineralized. As minerals replace the organism's original material, it can preserve the shape and sometimes even the cellular details of the original organism. This process is known as permineralization. Not all body fossils are preserved this way. Some are preserved through a process called carbonization. This is where heat and pressure reduce the organism to a thin film of carbon, and this is often how plants, fish, and soft tissue are preserved. Let's dive into some examples. Perhaps the most well-known body fossils are dinosaur bones and dinosaur teeth. These fossils can give us an idea of the size, shape, and lifestyle of these ancient creatures. But fossils aren't just about dinosaurs. Ammonites are probably the most commonly found body fossils in the British Isles. The fossilized remains of ferns and other plants are classic examples of carbonized fossils that tell us about prehistoric climates and environments. Body fossils provide a direct insight into what organisms looked like millions of years ago. They are like puzzle pieces from the past. Each one doesn't just represent an ancient life form, but also holds the story of its life and its environment. They are our most direct link to understanding life as it was millions of years ago. Chapter 2. Trace fossils. Trace fossils, unlike body fossils, don't record the physical structure of the organism itself, but rather a creature's activity and behavior. They can capture the day-to-day lifestyle activities of creatures that lived millions of years ago. For instance, the best example of a trace fossil are the footprints, or trackways, left by dinosaurs. Imagine a dinosaur took a stroll along a muddy shoreline. It left behind footprints that hardened and fossilized over time. These footprints, now solidified in stone, can tell us a lot about the dinosaur that made them. By measuring its footprints, we are able to tell the size, weight, and even speed the dinosaur was running at. We can tell if it was a single individual or part of a herd. Most of our knowledge of dinosaur behavior has come from the study of dinosaur footprints. Trace fossils aren't just limited to footprints. Fossilized burrows made by organisms such as worms or insects can also be preserved as trace fossils. Even the feces, poop, can be fossilized. The polite name for fossilized poo is coprolites. Coprolites can tell us important information about what things a creature was eating and how it digested its food. The beauty of trace fossils is that they provide a snapshot of life in the past. They give us insights into the behavior and activities of creatures that roamed the earth millions of years ago. Through trace fossils, we can piece together a more comprehensive picture of ancient ecosystems and understand how different species interacted with each other and their environment. Chapter 3. Index fossils. These are fossils that are so significant, they define a particular span of time in Earth's history, known as a geological age. Index fossils are commonly found species that are widespread geographically and existed for a relatively short duration. Scientists can use index fossils to correlate and date the age of rock layers in different locations, helping to establish relative geological timelines. For instance, if a particular species of trilobite is found in a rock layer, and that species is known to have lived during a specific period in Earth's history, then geologists can use the presence of that trilobite as an indicator of the age of the rocks that it is contained within. Index fossils play a crucial role in relative dating, where the age of rocks is determined concerning the presence of these fossils. Index fossils, therefore, act like bookmarks in Earth's timeline, helping us understand our planet's rich and fascinating history. Chapter 4. Transitional fossils. Transitional fossils, often dubbed as the missing link, are fossilized remains of life forms that exhibit traits typical of both its ancestor and its derived descendant. They are like snapshots of biological evolution, providing direct evidence of gradual transformations over millions of years. For instance, fossil lungfish show features of both fish and early land-dwelling creatures. Such a fossil bridges the gap between aquatic and terrestrial life. It's like a fish out of water, quite literally, with its gills, scales, but also with a robust ribcage and finger-like bones in their fins. Transitional fossils are invaluable in piecing together the complex puzzle of life's history. They help us to see and understand the evolutionary steps that species have taken and how life has diversified over time. Transitional fossils are the missing links in the evolutionary chain. Chapter 5: Wood and Amber. From wooden relics to bugs trapped in amber, nature's time capsules await you. Let's venture into the world of fossil wood and amber. Fossil wood, as the name suggests, is the remains of ancient vegetation that has turned into stone over millions of years. This process, known as petrification, happens when wood gets buried under sediment and is protected from decay by oxygen and organisms. Over time, groundwater rich in dissolved solids flows through the sediment, replacing the original plant material with silica, calcite, and pyrite. The result? A rock-like substance that preserves the structure of the original wood, right down to the microscopic cellular level. Fossil wood provides us with a record of the flora that existed in ancient ecosystems, helping us understand climate change and evolution. Amber is fossilized tree resin. This sticky substance served as a tree's immune system, sealing off injuries and preventing infection. When the resin hardens over millions of years, it first becomes copal, and then later it becomes amber. But here's where it gets really interesting. Sometimes the resin can trap insects, plants, or even small animals before it hardens. These trapped organisms, perfectly preserved in amber, provide an incredibly detailed snapshot of prehistoric life. Imagine an ant going about its daily business suddenly enveloped in a drop of resin. Fast forward a few million years, and we can study that ant in exquisite detail, right down to its antennae and legs. It's like having a time machine that allows us to peek into the past. Fossil wood and amber tell us stories from Earth's history. They give us clues about the environment, the climate, and the organisms that existed millions of years ago. Each piece of fossil wood and each amber nugget is a chapter in the book of our planet's history. These natural time capsules offer a unique window into the past, and every discovery brings us one step closer to understanding where we came from, and perhaps where we are heading. Chapter 6: Microfossils. Microfossils, as the name suggests, are minuscule remnants of microscopic organisms from prehistoric times. Despite being smaller than a grain of sand, these tiny fossils are a colossal source of information. Microfossils include a variety of forms, such as foraminifera, diatoms, and radiolarians. Foraminifera are tiny single-celled organisms that possess an intricate spiral shell or test. These tests can provide valuable information about past environments. The study of foraminifera is vital not only for understanding Earth's past, but also for monitoring contemporary marine environments and assessing the impact of environmental changes on these organisms. Diatoms are algae with glass-like cell walls. Their abundance and diversity provide clues about prehistoric water conditions. Changes in diatom populations can reflect shifts in water chemistry, nutrient levels, and overall ecosystem health. Their study is therefore crucial for understanding the dynamics of aquatic ecosystems, past climate conditions, and current environmental health. Radiolarians are tiny marine protozoa that have ornate silica skeletons. Radiolarian fossils can be found in sedimentary rocks, particularly in deep-sea sediments. The study of radiolarian fossils is essential for understanding past oceanic conditions, such as paleotemperatures and paleoceanography. Microfossils are therefore of critical importance as a reservoir of paleoclimate information and are also commonly used by biostratigraphers to assist in the correlation of rock units. Chapter 7: Tar fossils. Natural tar pits, such as the La Brea tar pits in Los Angeles, are known for preserving the remains of animals that have become trapped within the tar. This sticky, viscous material has an uncanny ability to preserve organisms in near-perfect condition, making it an invaluable resource for paleontologists. Tar fossils provide snapshots of prehistoric life, capturing everything from mammoths and saber-toothed cats to tiny insects. Understanding tar fossils helps us piece together the Earth's biological history and the evolution of life on our planet. Chapter 8: Subfossils. Subfossils are a fascinating class of fossils, not quite old enough to be considered full fossils, but still significant in their own right. They are typically less than 20,000 years old and have not undergone the same degree of mineralization as their older counterparts. This means they retain more of their original organic material, offering a unique insight into more recent history. The best examples of subfossils are the Ice Age remains found in the North Sea or in Siberian tundra. Subfossils are particularly important in the fields of archaeology and ecology. They can be found in environments where the conditions for fossilization are not optimal, like caves or peat bogs. From mammoth bones in the Siberian tundra to Neanderthal remains in European caves, subfossils provide a wealth of knowledge about extinct species and past ecosystems. While subfossils may not have the same age or mineral content as traditional fossils, they play a crucial role in our understanding of recent historical and ecological changes. So let's wrap things up. We've journeyed through time and explored the fascinating world of fossils. We have discussed body fossils. We have learned that preserved footprints can yield insights into the lifestyles and behaviors of past animals. We have discovered index fossils, which are used as time markers, pinpointing specific periods in Earth's history. We have also marveled at the role transitional fossils play in the story of evolution and life on Earth. We have learned how fossil wood and amber can give us snapshots into ancient ecology and environments, the very essence of lost worlds. We have learned how even the smallest microfossils can be important to our understanding of our planet's past. Subfossils, though not as old as normal fossils, help bridge the gap between prehistoric times and the present. Our journey doesn't end here. There's always more to discover, more mysteries to unravel. The world of fossils is as vast and varied as the life they represent. We hope that you enjoyed this fossil adventure. If you did, please like, subscribe, and leave a comment in the comment section below. Your support is appreciated. And we hope to see you on another episode of Fossil Fundamentals real soon. Keep exploring, keep questioning, and remember that every rock has a story to tell, every fossil a secret to reveal.